Hi, and welcome to MSc. In today's lesson, we're looking at an alternate example of determining the components of a vector. So here we have a vector v, which is a velocity vector of magnitude 2.3 meters per second with a direction of 78 degrees west of south. What I find helpful when I draw a vector is to picture a crosshairs, kind of like a compass rose, and to base the vector from that. This doesn't have to be perfect, but the better drawing you can make, then the better proportioned your solution will be and look on the page, which is always nice. It allows you to do a bit of a self-check. In this case, we are going west of the south direction. Well, by convention, south is down and west is to the left. So if we went straight down with our vector, that would be south, and to the left would be west. We're 78 degrees west of the south direction, so that would be about 45. This would be 90 degrees. We are looking somewhere, perhaps, at an angle something like that. Again, it does not need to be perfect at all. The angle we have found, which we could label here, this angle is our 78 degrees. We now have two components that we can sketch and draw. We have a vertical component and we have a horizontal component as before. We're choosing those because they are orthogonal components to one another, and that makes our math a lot easier and more reasonable generally for the types of calculations we want to do. This is then our vector v, our velocity vector. What we have produced here is a vy and a vx. The reason why I wanted to include this example in the video series is because this is an example where vy, the y component, is the adjacent component. So when we go to create an equation for vy, we are going to be using cosine because this again is the adjacent side. In the past, we've looked at examples where x direction is the adjacent, which probably is more common, but certainly not all the time, as we can see here. We always multiply by the hypotenuse, which is the velocity vector v. It's really just the magnitude of it. We can then substitute in and say 2.3 cosine of 78 degrees. And again, I would be tempted to leave it like this if I'm going to use it in other work or other steps of a problem. But if you were asked to actually find the size of the y component, then you would solve that using a calculator. And you'd record a few decimals. Again, we would round if we were asked to find just the size of this. There's two significant figures here, 3 in this part. I would be inclined to record this to 2 significant figures, and the units are meters per second. We can repeat this now for the x direction. It's going to be the hypotenuse v times the sine theta. And sine theta is 78, and we can see now we're the opposite side, even though we're the x component. This will be 2.3 sine of 78 degrees, which, again, I would leave if I'm going to do other work. Otherwise, I would write down an unrounded version of this. I like to use the ellipses indicating that it continues on, and I would round this also to 2 significant figures. And this would be meters per second. So this is breaking this velocity vector into its two parts. It has a y component that represents a velocity of 0.48, approximately meters per second, and an x component that represents 2.2 meters per second. Again, this is a great alternate example illustrating that x doesn't always correspond to cosine. It can correspond to sine, but sine will always correspond to the component vector that is opposite from the angle, whereas cos will always correspond to the component vector that is adjacent to the angle. I hope this has been helpful. Thank you very much for listening, and as always, thank you very much for watching.